So in last lecture, we saw how to write linear equations as a matrix equation. So over here, A is the matrix of coefficient, X is a vector, column vector, which carries the unknowns, and B is a vector of constants. And we also saw how to multiply a matrix with a vector, and we did it in two ways. One of the ways was, so you have a m by n matrix, you can multiply it with an n component column vector. So the number of columns in your matrix should match with the number of components in the vector you are multiplying with. Otherwise, you can't multiply. So the first way was that think of this matrix as made up of row vectors, and then you just take the dot product of your vector with which you are multiplying this matrix with each of the row vector. So the first way is as a dot product with row vectors. And as a result, you get a column vector of dimension m. So the dimension of the resultant vector is changed. It's not the same as the original vector. And over here, I've just explicitly written out the above dot products. The second way was that you think of your matrix as composed of column vectors. And then the rule is that you take your components, you have the same number of column vectors as the components in the vector with which you are multiplying, and then you just make the linear combination of all these column vectors with the components in your vector. So as a linear combination of column vectors of A to components of B. Can you speak up? Now, using this idea of multiplying a matrix with a vector, we extended it to thinking of matrix multiplication as similar kind of operations. So if you have two matrices A and B, the number of columns in A must match with the number of rows in B if you want to multiply them. So the first way is rows into columns. Think of the first vector as composed of row vectors, the first matrix as composed of the row vectors, and the second matrix as composed of the column vectors. Then what you are doing is going column by column. Take these rows and think of this like you have this matrix and you're multiplying with it with this column, first column, using the rule which we saw above. So this is a matrix written as columns, and then you just apply the rule, and the rule was that take each row vector and multiply with your column. Take the dot product with the column vector. So that gives you the first column. Then you do the same thing to the second column, B2, 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 all the way until you reach the last column. And you can see that over here, you're making dot products with the last column over here. So as dot product of row vectors of A into column vectors of B. Then we saw that we can also do it using the other rule. Again, I'm going column by column, but this time I take this column and think of the first matrix as composed of column vectors, and then apply the rule that take the components in your first column and make a linear combination of these vectors, like over here. Then take the second vector in your second matrix B and using these components make the linear combination. All the way until you reach this last vector, you take the components which are over here and again make a linear combination. And once you write it out, you will have your matrix multiplication. So what we're going to do today is look at more ways. Well, actually, I'll just discuss one more way which will be very useful to think of multiplying these matrices. And then writing these matrix multiplications as sum of components. This idea which we have said in words, we would like to write them as some equations. And using this notation of matrix multiplication as sum of components, we will be able to derive and prove many properties of matrix algebra. So that's the plan for today. So before I come to this part, let's just think about some easy operation. That what happens when I multiply a column vector with a row vector. I know that when I multiply a row vector with a column vector, I get a number. That's just the dot product. But this is not the dot product. You're taking column first and row second. So this is also given a name. It's called the outer product. So what does outer product give? This is just some kind of a practice with matrix multiplication. So suppose you have a column and you multiply it with a row. So you have something like that. You can think of it as a matrix. This matrix has m rows and only one column. So column vector can be thought of as a matrix of dimension m times 1. And you are multiplying it this can have any number of components. This is a row, so it has one row and n columns. And since these two numbers match, so we can still multiply them. And if I use the rules of matrix multiplication, I can do it in many ways. If I think of it as rows, so this row vector, this is again, I can think of it as composed of rows, but this row vector has only one component. It's a one-dimensional row vector, the first row vector over here. And I'm dotting it with the first column. And the first column over here has only one component. So the rule tells me that the dot product is just this. And the first column is made up by taking all these dot products where you don't even have a sum now. Again, taking these rows and dotting with the columns. All the way till you get so as expected. So you have to be clear about it that a row times column is a number, but a column times row is a big matrix. You get a m by n matrix. Now let's look at what happens. We have seen how to multiply a matrix with a column. Let's see what happens if I multiply a row with a matrix. I'm multiplying it with a matrix, but since it's a matrix, I can write it as a bunch of column vectors. As long as the dimension of these columns is n, I can multiply this row. And the rule is that I'll get so let me expand it out. Let me actually write it like this, just to derive the rule. Let's write it as A11, A21, this is M, and let's call it M, let's call it N, this is A12, A22, until you have AM2, and over here you have A1N, A2N, all the way to AMN. Now if I use the rule of matrix multiplication, I know that I'm gonna get this is 1 by m and this is m by n. So this is one row, it has only one row, this one, and I just take the dot product. The rule says take the dot product with this first column. So I get A11 plus A21 plus all the way M A M1. So whatever your row is here, that's what the rule says. Take the dot product. Gives you a number. Then you do it, this is your first column, and first column has only one number, one entry. Then you take the second column and again make the dot. Which gives you again some numbers, all the way until you go to the last column. And let me write that out explicitly. This gives you these numbers. W1 A1N plus W2 A2N W M A M N.
Sir, could you read this entire bracket out once, please?
So I used the rule. Take the rows and make a dot with each column. So I take this dot with this column, I get W1A11 plus W2A21 all the way to WMAM1. And then excuse me, then I was looking for then the next row, but there's no next row over here. So I'm done with this column. I just get one number in the first column. Then I pick up the second column and again start making the dots. That's over here, W dot V2.
Oh, so there's like a space here, like
Yeah.
a matrix, like a row.
Yeah,
right?
yeah.
So you want
So this gives me back numbers, n numbers. So I have got back a row. But its dimensionality changed from m to n. Which is fine because that's what happened in case of column. We multiplied a column from the left by a matrix, its dimensionality changed, but I got back a column. In this case, I multiply a row from the left to the matrix and I get back the row. It's just that its dimensionality is changed. It picks up this m from this n from the matrix. But I can think of it, looking at these numbers, I can think of it in another way. So I look at this row, this first component. What's happening over here? I have W1A11, so this guy pairing with this guy, and W2 with, then I look in over here. I'm going to have a W2. The first term from over here is W, so it's W1A12, and then W2, it has this term, W1A12, that's how it starts. But it also has a W2A22. This is how it's starting. So I have a W1A11 and a W2A21. So all of this I can write like this. I think of this row in this matrix, and I'm multiplying this row by a W1, by just a number. So I'll get back the row with W1A11, W1A12, all the way I get W1A1N. But I construct a row, but that row is only composed of W1 times the first row. Then I have other numbers. What are those numbers? I pick up this number W2 and multiply it with the second row over here, and then add that row. Then the third number over here, multiply with the third row, all the way to the last number. So I can write it as a linear combination of the rows of the second matrix. I was using M, yeah. So you have M rows in your matrix B. You are making linear combinations of them. So ये आपका A है, it has a bunch of rows. ये आपका B है, it has also a bunch of rows. What you do, you make linear combination of these rows through the components of each row over here. Like I've written over, like over here. Oh, well, I'm just doing for now just one row. You had one row, you take all these rows and make a linear combination like that. And you get back a row. You get back this row. So what we have interpreted it as a linear combination of the rows of B. Let's call this was a vector, row vector, through components of the row you are multiplying with. So once I have this, I can generalize it to matrices. If I have to multiply a matrix A with a matrix B, first we learned how to do row times vectors, row into vectors. Then we thought of them as vectors into vectors. Now we are thinking them as rows into rows. You have these rows here and rows here. You apply the rule, you start with each row over here in A, and you use the above rule how to get a new row. So you take this row and make linear combinations of the rows of B using this. That gets you the first row back here by making these linear combinations. Then you take the second row and use this to make the linear combinations. And that gives you the second row all the way until you have the last row and use that to make the linear combinations. And you have got your product. This is AB. Maybe we should do a small example. You have two rows and three columns, and over here, let's say you have three rows and three columns. So what's the rule? The rule says pick up your first row over here and make linear combinations of these row vectors. And that will be your first row. So what's the linear combination? It's 1 minus 1 0 plus 2 2 1 minus 1 plus minus 1 into the last row. And then take the second row and again make the linear combinations. 2 times the first row plus 1 times the second row plus 3 times the third row. So what do I get? I get, again, when I add the vectors, I add the corresponding components. So 4 plus 1, 5, minus 1. I get this row, which has a 4 plus 1, 5, minus 1, 4. At the second place, I get minus 1, plus 2, minus 1. So 0. And in the third place, I get 0, minus 2, minus 1, or minus 3. And then I have a row lying over here. 2 plus 1, 2 plus 2 plus 3, so a 7. Minus 2 plus 1 minus 1 plus 3, 2. 0, minus 1 plus 3, 2. So these are the two rows in my resultant matrix. So if I wish, I can write it out as a proper matrix. So that's the matrix plotted again. Linear combination of rows of B through rows of A. Linear combination of rows of B through.
Sir, I'm sorry, could you explain how you got 4 for the first matrix?
Rows of A. 4 where over here, yeah. So
Yes, sir.
so these are row vectors, and the rule of adding vectors making linear combinations is
Because I
that,
made a calculation error. I've got it. I made a calculation error.
so we have learned 3 methods of multiplying matrices. Dot product of rows of first and columns of second, and then linear combinations of the columns of first to the columns of the second, and the last one is the linear combinations of the rows of second through the rows of first.
Sir, could you please repeat the last sentence you said, please?
Last sentence is making linear combinations of the rows of second to the rows of to the components in the rows of the first.
Sir, do you mind scrolling it upwards? Just for a second, I need to make sure I've written everything. Thank you, sir.
Well, you can write it again. I mean, it's all recorded and uploaded. Even the notes are uploaded.
प्लीज जो लास्ट लेक्चर्स भी नोट्स थे वो आप अपलोड कर दे LMS पे भी प्लीज.
Okay. Now, there is a very nice notation which is very useful. Is if I have a matrix A, you say that Aij is just the entry in A at ith row and jth column. So for example, if I have this matrix, I can write, so what would be C23? It's just the number in the second row and third column. So this guy. So it's 2. What is, let's say, C13? First row, third column is 3. What is C33 is 0. This guy. So you can notice that knowing all these components, knowing all aij's for a matrix A is equivalent to knowing the matrix. That's what the matrix is. It's entries. So if you have all the list of aij's, you know the matrix. So a matrix is completely characterized by these entries. So this fact we can use to great advantage. First of all, let's write what is the matrix product. Matrix product as a sum. So if you have matrix A, let's say this is of type M cross P, and you're multiplying it with a matrix B of type P cross N, and I get a matrix back. So I would know this matrix C, product matrix, if I know all its components. And I want to write down what these components are in terms of the components of A and B. So by the way, because C is A times B, most often you just write it like this. That the components of the matrix which you get by multiplying A and B. So what are those components? I'm just using one of those rules. So let's just use the first rule. That like the first guy you get by taking the first row and dotting in the first column. And you get at the 1, 2 entry, you get it by taking the second row and dotting into first column. So that means at the 2, 1 entry. So that means the components, the ith, jth component, since it's a dot product, and in the dot product you sum over multiplication of corresponding components. Is this. I've just written out the dot product and as a sum symbolically. Nothing new over here. But using this notation, we can prove many results. Well, this is an extremely useful notation, but just a caution that if I write it like this, So this is again, and many a times, because I know that the columns here must match the rows in the B, and if it's understood that what is the dimensionality of those, sometimes I don't even write where I'm going up to what number. So you just write a sum over this K. All possible values of K. So when you write K, that means sum over all possible values of K. This is exactly equal to because that K over there just serves the purpose of summing different components. You could give it a name L, M, anything you like. So these two things are same. So you say that this K or L is a summed index. Another name, some people call it dummy index. So it's summed over, so it's gone. Gone, or does not survive in the sum. On left hand side. But this equation is not same as if instead of I, if I take because I was fixed. If I change I to M, I am taking some other component. But the summed index, that you can call it anything because it's just you are going over all the possible values. But I up there is fixed, which is not equal to M. So those two things are not same, but the summed index you can call it anything. Now using this notation, we can prove many results which you, let me see which one to prove. Okay, so let's prove this one, the easiest one first. Yeah, let's do this distributive law. For matrices, this is true. So I'm just gonna go real slow. This is a matrix, this is a matrix. So and matrix product, I'm looking at the matrix product of this guy. I'm looking at whatever matrix I get by doing this operation, what is its ith, jth component. So because I and j are arbitrary, if the ith, jth component of the left hand side is equal to ith, jth component of the right hand side, that means all their components match. That means they are the same matrix. But my formula above tells me if I have to find the ith, jth component of the product of two matrices, I need to do, let me change the color. I need to do this summed index but when I take the sum of two matrices, what is the rule? Adding two matrices is adding the components, corresponding component, adding the, if I take the Lth jth component of B plus C, that would be equal to Lth jth component of B plus the Lth jth component of C. That's the rule. So I can write it like now these guys, these are just numbers because these are entries in matrices. So for numbers, obviously this distributive rule holds. So I can multiply it through inside the bracket. And now I have a sum with two entries. So these are just a bunch of additions. So I can break the sum up into two sums. Because when I'll do this double sum, obviously I'll get all these entries back because there's already a sum over there. But this is the formula. This says that this is the ith jth component of AB. And this says that this is the ith jth component of AC. But I know that if I add the ith jth component of two matrices, I get the ith jth component of the sum. That's the very definition. So this is the ith jth component of AB plus AC. So that means I have proved that A times B plus C is equal to AB plus AC. But let me do slightly more complicated. It will involve a little bit more technique. The associative law, that you can freely move around these brackets. If you have three matrices and you're multiplying, you can first multiply B and C over here. Whatever the result you get, you can multiply it with A, or you can first multiply AB and then multiply with C. So how will you do it? So A, B, C, this ith jth component AIL, B, C, L, K. But then I have to look at what is the Lth kth component of BC. So that formula I know. That's just I introduce ith jth. This is J. So I introduce another dummy variable, let's say K, and L is fixed. In this element, L and J are fixed. So now I have a sum and a number is multiplying that sum. You know what does it mean? It means this number can go in. So I get summation L, summation K, AIL, BLK, CKJ. No, it's a double sum. You're just told that you have to sum over L and sum over K. So it's up to you, whichever index you sum first. Doesn't matter at all. So I can change the order of summation. And since these are just some numbers, I can multiply these two guys first. And leave it like that. But this, I have a repeated index L, which is being summed. So this is just ith, kth component of A product B. That was the definition of the product. And I have a kj here. But this is just the definition of ith, jth component of this matrix multiplied with C. So you have proved, because the ith, jth component of the two sides match, that means the two matrices are same. So these techniques prove to be very useful. Another interesting application of this technique is some properties of the transpose. So what's the transpose of a matrix? You exchange is a matrix with rows exchanged with columns. So that means, by definition, if I have a matrix A and I make its transpose, its ith, jth component of the transpose is equal to the jth, ith component of the original matrix, because I exchange the rows with columns. The number which you find at, let's say, second row and third column in A would be same number as in the third row and second column of A transpose. So A transpose, let's say, just for example, 2/3, 2 is same as A32. That's the definition. Whatever number you have at the second row and third column, or let's say over here, third row and second column in A, you take it and put it at the second row and third column, and that would be your transpose. Transpose तो सबने देखा हुआ है. I don't think I need to write an example, or do I need to? Should I?
Yes, sir, please.
All right. So let's say and I want to take the transpose. This is A. So A transpose. I take this row and make it a column. Take this row, make it a column. Now if I look over here, what is, let's say 1, 2. First row, second column, I have a 3. But in the transpose, that same number is at second row, first column, because I exchange those two things. Similarly, you can check other things. A2, 3. Second row, third column. That was a 2. In the transpose, Third row, second column is the 2, and so on. Third row, second column.
Sir, why not row 1, column 1? वो भी तो 2 है.
वो तो इत्तेफाक से 2 है ना, तो you will get, if I check this, which is a 2, in the transpose I'm exchanging 1 and 1, but I still stay at the same place. So I still get a 2.
Okay. Okay.
So this is a property of transpose, that if you have A times B, you make this product and compute its transpose. That would be equal to taking the transpose of B and multiplying it with transpose of A in the reverse order. And you can again prove it using the same techniques. So what's the, you have AB transpose, some matrix which you have gotten by multiplying A and B and taking its transpose, and you are looking at its ith, jth component. So if it's the ith, jth component of the transpose of this matrix, this must be equal to jth, ith component of the original matrix without the transpose. But this is just, according to our techniques, this product can be written like this. And this I can write, if it's the lth, ith component of B, this is also equal to ith, lth component of transpose of B. And since this is the jth, lth component of A, this is also equal to lth, jth component of transpose of A. Now I see that this I is a row which matches with this row, and this J is a column which matches over here. And since these are numbers, so I can write this like that, just for the ease of reading it off. They're numbers, so I can easily write them one after the other, doesn't matter. Numbers commute. So what is this? This is just the ith, jth component of the product of these two matrices. So I have proved the ith, jth component of AB transpose is equal to ith, jth component of B transpose, A transpose. So those two matrices are same. So I proved my assertion. Now let's consider the inverse. Before inverse, let me just write what is identity. So it's a n by n matrix. It's a square matrix with 1, 1, 1, whatever the dimension is on the diagonal, and zeros everywhere. So the components of this matrix you write with this symbol. This is called the Kronecker delta. And these symbols just means that you just give this rule that you get a 1 if I is equal to j, and you get a 0 if I is not equal to j. So like on the diagonal, if you have I2, 2, second row, second column, that means you're on the diagonal, you get a 1. If you have I2, 3, you're off diagonal, then you have a 0. But the same guy, since I know that all matrices I can write as some column vectors or row vectors. So if I write them as column vectors, they would be like this. It's a n by n, so n columns, each of n dimensions. And what is like, for example, E3 is 0, 0, 1, 0, 0. E1 is 1, 0, 0, 0. So EI, any one of them, with a 1 at ith place. So these are like unit vectors. So you can think of the identity as composed of unit vectors in your n-dimensional space. And if you want, you can also write them as rows. Even then you get the unit row vectors. Is also equal to unit row vectors. So for square matrices, I'm going to define an inverse. So A inverse is a matrix which gives identity when multiplied with A. So that means if I have a matrix A, I look for another matrix and I'm just giving it a symbol A minus 1 so that I get I. And this should happen if doesn't regardless of if I multiply it from the left or from the right. Well, actually you can prove that if you have found a matrix which gives you identity if you multiply it from the left, then it will also give an identity if you multiply it from the right. But the proof is very, very hard, so we're not going to do it right now. Now, it may happen. It is possible that there is no such matrix. No such matrix. There's no guarantee that you will have a matrix like that for a given matrix A. If that happens, then you say A is singular. There's some terminology. And if you can find, by find I mean if it exists. It's not about that if you are smart enough or not. If there exists a matrix with such a property that it multiplies A and gives you identity, then you say that A is non-singular. And if A inverse is the inverse of A, then A is the inverse of A inverse, because they act on both sides. So you can think of this as the starting matrix and think of A multiplying it and giving you an identity. So they are inverses of each other. So if A is non-singular, A inverse is also non-singular. I can prove a very easy theorem involving inverses. If A inverse, B inverse, if A inverse and B inverse are inverses of A and B, respectively, that means A and B are supposed to be non-singular because these exist. Then A times B is non-singular. Then the product is also non-singular and has an inverse given by B inverse A inverse. So you can compute the inverse. It's just the constructed out of the inverses of A and B multiplied in the opposite order. So consider this matrix. Right now we don't know if the inverse exists or not. So I just start constructing it. I just consider this guy. The claim was that this is inverse, so we just check it. So consider this matrix and multiply it with AB. The idea is that if you get identity back, then this matrix C is inverse of AB. Now that associative law comes very handy. I can change this order of these brackets. So I'll go one by one. This is one matrix. These are two matrices with a bracket around them. So I bring the bracket onto these guys. And leave B over here. Now I can use the associative law inside. Because I can change the order of brackets in the multiplication. But this, since A inverse was an inverse of A, so this is just identity. And identity with any matrix gives me back the matrix. I should have said it before. Again, since B is inverse of B, I get identity. So the conclusion is C, which is B inverse A inverse, is the inverse of AB. And it exists because you can just construct it. So the inverse exists and we know its form as well. Yeah, so I should probably put these two notes. For any A. And the proof is really simple because you are taking the dot products with unit vectors which do not change anything about these vectors. Or you can say that you are making linear combination with these unit vectors, so they do not change anything. And this part, probably you should prove it. This is not true in general. I think this is probably, इसको थोड़ा सा लिखने की कोशिश करते हैं, would be nice exercise. This is L and I'm writing AB ith jth component. If I write BA ith jth component, these two are not same. These two sums are obviously not same, because in the first sum you are fixing this ith row from matrix A and picking up its numbers to put in the sum. While in the second one, you are picking up the jth column of the matrix A and putting it inside the sums. And there's no reason for ith row and jth column of A to be same. Similarly, not only that, you have then the different rows and different columns coming from B in the sum, and they will also be in general very different from each other. So these sums are not same. So the two ith jth components do not match, and AB is not equal to BA. I have to move to some very important concepts, but I don't think I'll have time. So let me just say one final thing. Let's just start thinking about it. So again, as I said, that if you have linear system, you can write them as this kind of a matrix equation. And if you are given this kind of a matrix equation, you should think of it that is coming from some linear system of equations. So you're given this equation, and you know that, consider x hat, you're trying to find a solution of this equation. So what is a solution? Solution is some values for this matrix X, so that when you multiply with A, you get some values for this vector X, so that when you multiply with a matrix A, with this particular matrix A, you get back B. So consider X hat to be, because it's a vector, write like that, to be any solution of this equation 1. So it's a vector, a list of numbers which solves the above equation. And it's any solution, because we know that if we have a linear system of equations, we can have more than one solution. We can even have infinite solutions. So from that set, I pick up one solution. Then I can multiply both sides by a matrix. Well, for this case, it will be true for any matrix, but let me be specific and say non-singular, because then it will go both ways. Then I get MA X hat is equal to MB now. I'm considering over here square systems. So this will give me some new matrix, M times A. Let's call it N. And when I multiply this column with a matrix, I'm going to get back another column. And since B are known, M is known, I've just multiplied with the matrix by hand. So I'll get a known column over here. So this is a new system of linear equations. But since this guy solves this by solution, that means that this is true for x hat. That this is true. So if I multiply both sides of this equation by this matrix M, so I will get this. That means my original solution is solution. And remember, this x hat was any solution. Any solution of this original system is also a solution of the new system. I guess I should give them name. This system, let's call it 2. So any solution of 1 is also a solution of 2. What about the other way around? I have got this new equation. Consider 2. And consider any solution of it. Let's call it y hat. So that means it solves it. This is satisfied. But M, I said, is non-singular. So that means it has an inverse. So I multiply both sides by M inverse. But N was just M times, what was it, A. And C was just M times B. And because of associativity, these two cancel. It's the inverse of M, so I get this. Which implies that this y hat is also a solution of 1. So that means if I take any solution of 1, it's also a solution of 2. And if I take any solution of 2, it's also a solution of 1. So the solution set is same. So what do you call such systems? They're equivalent. They're no different. So that, but remember that to go the other way around, I had to assume that M is non-singular. This is going to happen only if M is non-singular, not otherwise. So that means if you have given a system written in this form, you can multiply it with any non-singular matrix, you will not change the system. Your solution set will not be changed. So you have this freedom. Keep multiplying with any non-singular matrix to get the systems which are simpler to solve. So we'll use this idea to implement the methods which we have discussed before, those row operations written in forms of matrices, and then again deriving solutions. Any question?
सर काइंडली ये लेक्चर नोट्स लेमस पे अपलोड कर दे प्लीज.
ठीक है. Okay, let's stop here.